share my screen. I hope it is visible.
Yes, we can see.
Okay. Now. Okay. So in these lectures, we will discuss one approach to describing the evolution of interacting particle system with a large number of particles in random media. We will discuss the following problems. Firstly, we have to understand how we will describe the large amount of interacting particles. Second one, after we get some valuable equation for such system, we need to prove that this equation has a solution with good properties. And after this, we will discuss the long-time behavior of solution. Because always when we have some dynamical system, we are looking in deterministic case for some stationary points where system remains to be forever, and discuss the character of these points, attractors, repelling, and so on. And in stochastic case, the analog of such stationary points is stationary behavior of the system when the probability characteristics of the systems organize a stationary sequence or organize a constant sequence or a constant function in case of stationary process. So this is our plan, and let us begin with understanding why we need some special language for large system of the parts. Let us consider some known example of equations for finite system of particles in Euclid space. This is a well-known Kuromoto system of connected oscillators. Here, phi 1 and so on, phi n, are the angles of oscillators, and they are connected in such a way, as you can see in this equation. This equation is interesting from different reasons. First of all, let us define the following measure based on the solution. So let us define for any t which is greater or equal than 0 such a measure which is concentrated at the points phi k. Here the symbol delta is related to the well-known Dirac delta measure. So the measure delta phi k is concentrated at the point phi k with the weight 1. But the normalizing multiplier 1 over n before the sum gives us that mu t n is a probability measure concentrated in n points phi 1, phi n. Then one can rewrite the initial equation as follows. You can see that differential of phi I t is equal to the integral of sine of the difference phi I t minus v with respect to this measure mu t n dv. And one of the questions is, what happened when n tends to infinity in such a way that mu 0 n approximate some probability measure? when n tends to infinity. So what happens with our equation? Which form it will get, and what is the solution of our equation for arbitrary initial measure mu0, and in which sense solution of initial equation will tend to solution of the limit equation. This is the main set of questions which we will discuss, but also let me go back to the initial equation. You can see that the right part contains only difference between different phi's. So it is very natural to say that one cannot expect actually excluding very rare case, one cannot expect the stationary point for all systems. And it is exactly what happened. The Kuramoto system of connected oscillators is well known for its limiting behavior, because its limiting behavior demonstrates something new, comparatively usual approach, which we are discussing in the theory of ordinary differential equation. So we will see that one can check the limiting behavior of Kuramoto system using the approach which we will consider in these lectures. But for today, the main question for us is, what happened if mu0n approximate arbitrary, not necessary discrete measure? What happened with equation, and what we will get as a solution, and so on. Another example also is, this example may be the one of the oldest one. This is the equation, Helmholtz system of infinitesimal vortices. This equation, or this system, was invented by Helmholtz in order to substitute Euler equation of liquid for liquid fluid. He proposed to substitute the liquid by the finite number of infinitesimal vortices placed in the points Ri. And you see the two-dimensional version. In this version, the equation for motion of such infinitesimal vortices looks like, you see this pk, this some physical constant, and you see gradient with the sign of orthogonality. It means that we calculate gradient of the function, then rotated anti-clockwise on 90 degrees. So again, if we denote by mu tn capital the sum from k equal 1 to n pk delta r k t, again Dirac delta measure concentrated at the point r k t, then one can rewrite Helmholtz system with the integral with respect to this measure mu and t dv. And the question remains to be the same. What happened if initial measure mu0n tends to some probability measure when n became to be large, and in which kind of equation the initial equation turns if mu is not discrete measure, it can be arbitrary probability measure, for example, like Gaussian standard distribution. The last example also gives us the same feeling. It is also well-known example which belongs to Dyson, Freeman Dyson. This is well-known his equation for non-colliding diffusions. you see the equation d psi it is equal to sum from k equal 1 to n, k does not equal to I. And here is 1 divided by difference dt plus db beta I, where beta is a standard independent standard linear processes. So again, what happens if we again introduce such a measure and say that initial mass distribution approximate arbitrary mass distribution. So what will happen with our equation, what will happen with our solution, and so on. This example shows us the problem. One can see that there are well-known cases where the system of the particles satisfy some equation which can be written involving empirical distribution of the mass of these particles, and natural question arises: what happened if this empirical distribution initially converge to some probability measure which is not discrete? So one can imagine that, for example, in Kuramoto case, we have a continuum number of connected oscillators, or in Helmholtz case, we have continuum number of infinitesimal vortices with different vorticity and so on. In order to solve this question, in order to answer what will be the kind of new equation, first of all, we have to create some tools to discuss this convergence of the measures. Of course, from the university courses, we know that there is a good convergence of probability measures, probability distributions, which is called weak convergence. Everybody remembers central limit theorem, where the statement include the weak convergence to the standard normal distribution. But this convergence initially is defined like a convergence of characteristic functions at every point, or distribution functions in any points of continuity. But it is desirable to have some distance between probability distribution in order to say, you see, this distance converges to zero, for example, in central limit theorem. Even this distance converges to zero with the same speed. And people, of course, did it, and there are a lot of different distances which are connected with the notion of weak convergence of probability distributions. For example, again with university courses, you know, Levy-Prokhorov distance. But for our purposes, it is good to have to work with such Wasserstein distance. And let me introduce this distance for you. Suppose that we consider the set of all probability distributions on Borel sigma field in R. I always will suppose that all our measures are on the Borel sigma field of RD on some other space. So in the future, I will know to emphasize this. But the first time, I just recall that in RD, we have a Borel sigma field which consists of all nice sets like closed, open, And we have here a set of all probability distributions. For example, in M, we have, of course, the combinations of delta functions with different weights, like we have seen before. Also in M, we have some continuous distribution, like Gaussian distributions, and so on. Now let us build the distance in M. For mu and nu, which belong to M, consider the set Q mu nu of such measures on RD multiplied on RD, which have mu and nu as their marginal distributions. So we have a product RD multiplied on RD, and we just consider such measures on this product that if we project this measure on the first coordinate, first RD, we get measure mu. And if we project on the second coordinate, we get measure. This set Q mu nu is always non-empty because for sure it contains at least product mu multiply nu, which is defined in the usual way. If you have a rectangle in RD multiply on RD, then the measure of this rectangle is equal to mu of one side multiply on mu of another side. So this set Q mu nu is always not empty, but it is very helpful to solve the full exercise to build some other examples of measures from Q mu nu. Now the main definition of Wasserstein distance. This is a distance of order 0. Gamma 0 mu nu is the infimum with respect to this space of like common distributions from mu of such integral. Here is norm u minus v, and in the denominator 1 plus norm u minus v kappa du dv. From the first look, this definition becomes to be, it seems to be very complicated. But let us discuss the right-hand side. First of all, look at the function which is inside of the integral. You see this ratio, and let me tell you that this is again a distance in RD. It will be a good exercise to solve it, but this is a distance in RD. Of course, with this distance, RD turns in some ugly space. For example, diameter of RD becomes to be 1, but still it is a distance. So what we just find such kappa that this distance is smallest. Another remark is the following: that this distance arises naturally when we discuss convergence in the probability of random variables. Maybe you remember that if we take expectation of psi n minus psi divided 1 plus norm of psi n minus psi, if this expectation tends to 0, if and only if psi n tends to psi in probability. So now we understand that maybe this quantity can be a distance, and it is related to some convergence of probability measures. Also, it must be noted that this quantity is closely related to a very interesting and intriguing problem of optimal mass transportation, and there are a lot of books devoted to this problem, and even sometimes this Wasserstein distance is called Kantorov distance because of the relationship with the mass transportation problem. But we don't, we will not go in this direction. The following lemma is well known. That it occurs that the set of all probability measures with this Wasserstein distance of order 0 is a complete separable metric space. Maybe we already believe that this is a distance, but how one can get separability and completeness. Separability comes into natural way. Maybe it is not surprising that any probability distribution on RD can be approximated by the discrete measures. We just take increasing partitions of RD and put points inside of the cells of partitions, and in this way we get discrete measures which approximate that. So this is a way how we find separability under Wasserstein distance. What is about completeness? As we said, maybe, at least we have some feeling, it is related to weak convergence, because this distance, which is inside of the integral, is related to the convergence in probability. But it is interesting to know that a weak limit of probability distribution is also a probability distribution. So we understand that maybe completeness of M gamma 0 comes from this reason. So let's go further. And it occurs really that convergence in the distance gamma 0 is equivalent to the convergence of probability measures. Namely, gamma 0 mu and mu tends to 0 if and only if for all f which are continuous and bounded, f of the integrals with respect to mu n tends to integrals with respect to mu when n tends to infinity. This was done for set of all probability measures. But maybe when you study probability in university, you get the feeling that it is slightly non-convenient to work with the convergence in terms of this all continuous functions. Even in terms of characteristic functions, excluding the case of sum of independent identically distributed sums. So it is more preferable to work with moments of the distribution. So in this way, we have the different Wasserstein distance of different orders related to case when the measures have some moment. So denoted by Mn, the set of probability measures on Rd, which have a finite nth moment of the norm. Definition. Here is the definition of Wasserstein distance of order n, which is greater or equal to 0. You see? You have the same approach. You have another distance. And now this is an n distance between, for example, random variables. And you just use this distance and get the infima with respect of all joint distributions of mu and nu. And again, it is not surprising that Mn and gamma with the distance gamma n is a complete separate metric space. The reasons are more or less the same as we discussed before for M gamma 0. Now what about convergence? Convergence in the distance gamma n is equivalent to what? How to describe the convergence in the distance gamma n as in previous case? For example, let us say that maybe some weak convergence plus something like that. In order to understand what happened, it is good to have characterization of compacts in both cases, mu mn and m gamma 0. So here is the answer. For example, in case of gamma 0, you know this well-known Prokhorov theorem that the closed set F in M is compact if and only if there exists a sequence of compact subsets such that over all this family F capital mu of the difference Rd minus Kn, what is remaining outside of Kn, tends to 0. Now note that this can be rewritten. As I said you, the rho 0 uv, which is equal to such ratio, is again new distance in Rd. Then one is equivalent to the following, that the sup of such integrals tends to 0. Now when we have such form of compactness criteria in the Wasserstein space of order 0, in the space of all probability distributions in Rd, this criteria can be very easy rewritten. Probability measures which has finite moment. Suppose that we have measures on Rd which have m's moment of the norm, and define now distance to the compact rho ku, this is infimum of norm of u minus v, where v belong to k. Then the closed set F in Mn is compact if and only there exists a sequence of compact subsets such that such sup tends to 0. You see, it is almost the same what we have in case of all probability distribution and Wasserstein distance of order 0. So in case of weak compactness, we just need that sup of integrals with this distance tends to 0. In case of all probability distribution which has finite moment, we need to have such sequence of compact that the sup of integrals where we have distance to compact in this in the m power also tends to 0 and n tends to infinity. Okay, and this is a characterization of compacts in the set of probability distributions on Rd relatively to different Wasserstein distances. Now maybe we understand that in initial examples of Kuramoto, Gary-Goltz, Dyson systems, we can say, okay, Let initial empirical distribution tends to arbitrary probability distribution in Wasserstein distance of order 0 or of order m. It depends on specificity of our problem. But then we need to understand what happened with the solutions, the solution as a measure valued processes. Let us go to the question. What about the criteria of compactness of the measurable processes? In order to understand how we can formulate the criteria of compactness of measurable continuous processes, let us reformulate the statements what we get. And let us do it as follows. General principle for description of compact sets in Mn for special is the following. For special decreasing sequence of functions Gn, you see Gn for M0. This is, for example, distances for two compact like a ball of radius m. And here is the again distances to ball like radius m, but in m power. Closed set f in Mn is compact if and only if sum of such integrals tends to 0. And we will use this general principle to discuss the compactness of continuous measurement value. The main question is the following. When the family of psi alpha of random elements in C01M or C01M indexed by M small is weakly compact. We get this question from the initial problem. As I said, suppose that in Kuramoto system, for example, we have the following situation, that the initial mass distribution approximate some continuous distribution. But then what will happen with the solution? Solution are elements in C01M. In which sense they will converge, or even do they converge or not? Yeah? In order to understand this, we need characterization of weak compactness in these spaces. So how we will do this? Before to introduce my approach, I must say that there are a lot of even books devoted to measurable valued processes where you can find the criteria of weak compactness, of course. Maybe one of the most known is the Aldous criteria of weak compactness for measurable valued semi-Martin. But in order to have weak compactness, we have to check some general properties. One is that maybe we need compactness for the fixed time argument, and second one is that we need some equicontinuity. In both cases, these well-known criteria are or closely connected with a special class of measurable value process, or use some heavy for checking conditions. I will tell you this in the future. So now let's go to our approach. Consider the sequence. Of functions fk, such they are finite with compact support, such that any function of compact support can be approximated of some element from our sequence. By the way, it will be a good exercise to construct such family. Also, Also, let us note that this Fk can be chosen smooth. So not only C0, but C1 0, C2 0, or even C infinity 0. Yeah? Okay. Now, let me present you the main theorem. The family Xi alpha is weakly compact in C01 Mn if and only if. For every k greater than 1, the family Fk Xi alpha du is weakly compact in C01. So we just take integral from those family of function Fk, of functions, take 1 and Fk, and it must be weakly compact. And second condition is the following. We organize family which depend on two parameters. One is alpha, is the parameter of our family of random measure-valued processes. And another one is k, this is a number of function gk. You remember this function gk are responsible for compactness in the space M or M small. So we need that this family, double parameterized family, is weakly compact in C01. And the third one condition, this condition is related to compactness and the fixed interval, fixed time point. And this is just convergence in probability to 0 of the remaining term. You remember these integrals from jk like remaining, like tails of probability distribution. So sup over alpha, this probability tends to 0. So I must say that most difference of this criteria with the known criteria of the literature is the third condition. Usually, unfortunately, third condition is formulated in such a way that this sup over alpha is under the sign of probability. And it's gonna be a problem. Instead of this, we have this condition too, where the family double parameterized must be weakly compact. So we move the difficulty to the condition 2. Yeah. Now let us consider the example of application of such criteria. Let us check that it works. I will not consider the chromotor voice system. We will discuss it in the next lecture, but consider the very interesting example. This example, by the way, is one of the source of the so-called McKinley equations of the mean field. Consider the sequence of independent standard Wiener processes in RD. Now, for any n, define the measure-valued process mu and t, which is equal to empirical distribution of this wkt. And let us. Here is a picture. Here is a picture. Let us consider it. So by the red color, I draw the trajectories of Wiener processes. They are independent. And what is mu en? It is concentrated in the black points as I draw in the picture. So now let us check that processes mu n are weakly compact in C01 mu mn for any m which is greater than 0. Let us begin proof from the conditions. Fix t which belongs to 0, 1 and epsilon greater than 0. Then this sup is equal to the following. And as we discussed in the beginning of the lecture, mu t consisting of delta measures, and the integral with respect to delta measure is from continuous function is the value of this function in this point. So we have such supremum that 1 over n this sum jk yj t is greater than epsilon. And this supremum we just use Chebyshev because jk are positive functions. And when we calculate expectation, I use it all w j are equidistributed. So we have such equality, such inequality, and one can easily see that for k tends to infinity, this expectation tends to 0. Yeah. Now let us back to the condition 2. As I said, here is the condition 2. As I said, this condition are most intriguing. Here we have a family of continuous random processes. For fixed alpha and k, we have the continuous process in which is an element of C0, random element in C01. We can consider the equicontinuity of these processes, and for example, fix the values at the point 0, yeah? Because we are working in R in C01. So this is not. It is not necessary to look for a special condition of compactness under fixed T. So let us go and think how we can guarantee the equicontinuity condition. The usual way is to apply Kolmogorov criteria. You know Kolmogorov criteria of continuity of random processes, that the expectation of the difference in some power, positive power, must be less or equal to constant multiplied by the difference of arguments in power which is greater than 1. There are two remarks there. The first one is that the same criteria works for equicontinuity. So if we have family of processes which satisfy Kolmogorov condition with the same constants, then if we fix the initial position at the time 0, the processes became to be weakly compact. This is one node, and another one is about Gaussianity. Maybe you remember a trick with Wiener process. When we discuss the continuity of Wiener process, it is enough to check its second moment. Why? Because the Gaussian variables have the highest moment which is controlled by the second moment. And if we say that second moment satisfies some Gölder, even Gölder condition with some power which is just positive, then we immediately have the continuity for Gaussian process. So I will use to these ideas. Why? Because in our case, functions jk are very specific. Let me recall you. Here is function jk. So if we discuss, for example, the difference of these functions for different points u1 and u2, then it can be estimated more or less by the m-1 moment of the random variable, and again we can apply that we will consider Wiener processes inside. They are Gaussian. So if we estimate the second moment, we can estimate highest moments too. This is the idea. Now let us consider what we can do. Here is it. Okay. Now let us check that this is weakly compact. This double parameterized family. Here is n, and here is k. And then for any k, let's consider expectation. Expectation has the following form. Here is pt is a Gaussian density with a parameter t and zero expectation. From this point of view, and just recalling that J1 is already equal to 0 inside of the ball of the radius 1, one can say that this expectation tends to 0 uniformly with respect to n and t when k tends to 0. So the expectations organize compact family. Since then, it is enough to consider difference between this sum of jk and its expectation. So I will check just variance. But when we discuss the variance of this difference in two different time points, t1 and t2, then we have a sum of independent random variables. So we have just such one variance, and this one variance can be, due to Cauchy inequality, estimated like t2 minus t1 with some constant. What does it mean? It means that now using almost Gaussianity of jkw, we can use Kolmogorov criteria, and we get the condition 2. Now look for condition 1. As I said, one can take these test functions fk not only with finite support, but with finite support and smooth. For us, enough if they have continuous derivative. Then, using the same arguments in case of condition 2, one can check the condition that condition 1 also holds. Now, we have the weak compactness of our distribution, of our measurable valued process. And now let us think about its weak limit. And maybe it's good to go back. It's good to go back to this definition. You see, this mu Tn looks like empirical process which is built from different independent realization of Wiener process. Since then, it looks that it must converge to non-random limit. It's natural. We have a law of large numbers. And we already proved that these measure-valued processes are weakly compact. So to get weak convergence, we have to look only what happened when T is fixed, T small is fixed. Let's do it. Here is our proof. Now note for fixed T, just use the law of large numbers. And one can check that mu Tn converge every sure with respect to Wasserstein distance of any order, by the way, to the normal distribution with parameters 0 and t. Consequently, mu n has a deterministic limit. Mu n has a deterministic limit, which is just Gaussian distribution with the parameter t when t moves on the interval 0, 1. This idea gives us a source, as I said, to so-called Makin-Vlasov equation for the mean field. And in future lectures, we will discuss the difference between the description of the system of the particles in random media and the system of particles which are perturbed by the families of independent minerals. Because in case of when we have a lot of independency, finally, as we have seen, we have deterministic. So let me make a resume of what we did in this lecture today. We prepare some tools for discussing the random measures and random measure-valued processes as an element of complete separate space of measures with Wasserstein distance. We know what is the Wasserstein distance of any order. Also, we discussed criteria of compactness in Wasserstein spaces and in the space of measure-valued processes of any order. So that's all what I wanted to present you today in my lecture. Thank you for attention. Maybe somebody have questions or comments, please.
I have a question.
Okay.
So what about the slides? Would they be available for the participants?
Yes, surely it will be available for the participants, yeah.
Okay, thank you.
You're welcome. Okay, if there are no questions, I just want to put your attention to lemmas, what were stated during the lectures. As Jana asked, the slides will be available, and it will be a very good and very useful exercise to prove the lemmas, to build some examples of measures from Q mu nu, and try to understand what is the distance between two special measures. Of course, we will do something related to this in the next lectures, but for better understanding, it is good to do by yourself. Thank you for attention, and bye.
Okay.
Thank you.
Thank you.
Thank you. Bye.
Thank you all for today's lectures and participants and lecturers. So see you tomorrow the same time or at the same place. So goodbye for today.
Thank you. Bye.